Sections 2.2 and 2.3, the first and second derivative rules and tests. Now, we say rules tests because sometimes they're called rules, sometimes they're called tests, but they're both the same. Okay. So, the first derivative rule goes like this. If you take the first derivative, for any values x that the first derivative is positive, then we're going to say that the function f of x is increasing on those intervals. Now, when we say that it's increasing, we do have to be careful because I'm going to sketch some examples, but I'm not limited to this. All that I'm saying is that if I'm looking at the graph from left to right, the point to the right is going to be a little bit higher than the point on the left. That's all. So a couple of examples, it could look like this, it could look like this, it could be just a straight line. Okay, so as long as you're reading the graph from left to right, what really matters is that the point to the right is higher than the points on the left. That's all. And so that's what we mean by increasing. Similarly, if the first derivative for any x value is less than 0, then we're going to say that the function f of x is decreasing. And so once again, all that matters is if we read from left to right, the points on the right are lower than the points on the left. So we could have concavity, either direction, or you could just have some sort of line that decreases, okay? So decreasing as we go left to right, the points on the right are lower. Now when we talk about second derivative, so if the second derivative for any x value is positive, that is greater than 0, then we're going to say that f of x is concave up. And of course, concave up really in some form or fashion is a smiley face, okay? So it's a bowl shape. But then if the second derivative f double prime of x is less than 0, or negative, then we're going to say that on those intervals where that's true, f of x is concave down. And that's really the frowny face, or a hat, or upside down bowl. But concave down looks like that. Now, let's make some notes here. This rule says nothing about what happens when the first derivative is equal to 0. Okay? If the first derivative is 0, essentially it's inconclusive, or you need to check it. Alright? Now, the same thing about second derivative. This rule says nothing about what happens when the second derivative is equal to 0. And so when the second derivative is equal to 0, these are points of interest for us. Okay, they could be something that's applying in these tests, but they may not. All right, so we just have to be careful and understand that the rules don't tell us anything about what happens at 0. But I claim that you can actually use those 0 points as points of interest. And so, in general, if you want to find the relative extreme points of any function, then what you're going to do is you're going to set the first derivative equal to 0 and solve for x. Well, once you've found those x values that allow the first derivative to be 0, what I'm going to say is let A represent the zeros of f prime. Now, if we let A represent the zeros of f prime of x, then what I claim is that if you know that f prime of x is positive to the left of A and negative to the right of A, then what actually happens is, well, you would actually get this image, where specifically that's the value where x is equal to A. And so if that's the value, then we know that there exists a local maximum, a local max, which is the same thing as a relative max, at x equal to A. Similarly, if you look at the A value, and you pick a value to the left of A, plug it into f prime, and you get negative, then you would know that to the left of A, the function is decreasing, and then if you picked a value to the right of a and plugged it into the first derivative and it were positive, then you know it's increasing on the right, and so then we would say that we actually know we have a local min at x equal to a. But really, to confirm what I just said about that first derivative test, we can use the second derivative, because remember that the second derivative is actually going to give us concavity. And so what will happen is that if you know that there's some point A that's the zero of the first derivative, then essentially you know you have a flat spot of some variety. You have a flat tangent line. And so that's either going to be a peak, a trough, or you have to be a little bit careful because the weird spots where it flattens out, but it's neither a maximum nor a minimum. For the record, I'm thinking about things like this, like x cubed. There's this weird flat spot in the middle that happens, but it doesn't actually become a maximum or a minimum. And so with that being the case, we need some other way to verify our local maxes and our local mins. And I claim the answer to that is the second derivative test. Because remember, if I take the second derivative and I were to plug in a at that value, if I plug in a and f double prime of x is positive, then we know we have concave up for our original function f of x, where specifically there's some a value down here, and that we know now is a local minimum. And so in conjunction, you can use the first derivative test to find possible relative extrema, and then you can use the second derivative test to verify whether that is a local minimum, or in the situation where f double prime is negative, of course that's concave down, and so then that would force a local maximum. And so that's exactly what we're going to do. We're going to use the information from the first derivative to figure out possible local extrema. Then we're going to use the second derivative to say, oh, I know, yes, this works. No, this doesn't. Yes, this works, and it's local min, or it's local max. Or if you have an inflection point, you'll have to inquire further. So, I claim that the graph of the following has two relative extrema. Let's find and classify these points. So, step 1. We need to take the first derivative. So let's find f prime of x. Well, f prime of x is going to be negative 3x squared plus 2 times 3 is 6x plus 9. Derivative of 1 is 0. There's our first derivative. Well, now, the first derivative test says set this equal to 0. That's negative 3x squared plus 6x plus 9. Personally, I'm going to factor out the negative 3, so this is 0 is equal to negative 3 times x squared minus 2x minus 3. Then I'm going to factor this as 0 is equal to negative 3 times x minus 3 times x plus 1. Then to verify my correct factoring, 1 times negative 3 is negative 3, good. 1 minus 3 is negative 2, good. X times x is x squared, this works out. Then zero product property, 0 is equal to negative 3, that's a no solution situation. 0 is equal to x minus 3, 0 is equal to x plus 1. Then I get that x is equal to positive 3, and I also get that x is equal to negative 1. So now I claim that the possible extrema, and sometimes these are called critical values, are x is equal to negative 1 and 3. Now, when I say possible, I made sure I said possible because I can't guarantee that either of these are extrema, but they may be. And so how can we check further? Well, I claim let's use the second derivative. So, let's find f double prime of x. Well, f double prime of x, that's going to be negative 6x to the first plus 6. Now at this point, I want to evaluate f prime of these critical values. F double prime of these critical values. So, let's find f double prime of negative 1. Well, f double prime of negative 1 is negative 6 times negative 1 plus 6. Negative 6 times negative 1 is positive 6. 6 plus 6 is 12. And so what that tells me is that f double prime of negative 1 is positive. Well, then that I have f double prime of negative 1 is greater than 0, that's a concave up situation. And so thus I know that at that a value negative 1, I must have a local minimum. And so specifically, this must be a local or relative min. Great. Then let's check the other. F double prime of 3. F double prime of 3 is negative 6. Negative 6 times 3 plus 6. But negative 6 times 3 plus 6 is going to give me negative 12. And so because f double prime of 3 is negative, I know that at the value 3, at the x value 3, the function's going to have a concave down situation, right? And so then I can guarantee that 3 here is a local max. Now, that's just the location of those local mins and local maxes. If I actually want to find those local mins and local maxes, of course I do need to plug it into my initial function, and we can do that real quick. So f of negative 1 is going to be negative 1 quantity cubed plus 3 times negative 1 quantity squared plus 9 times negative 1 plus 1. Well, that's going to give me 1 plus 3 minus 9 plus 1, which is negative 4. So now I know that specifically I have a local min at the ordered pair negative 1, negative 4. And we can find the local max similarly. That's going to be f of 3, which is then negative 3 cubed plus 3 times 3 squared plus 9 times 3 plus 1, which I get as negative 27 plus 27 plus 27 plus 1, or 28. And so then I know that I have a local max at the ordered pair 3, 28. Now a couple things to note. Notice that when I found the actual local minimum and local maximum, the ordered pair has to come from the original function. The first derivative just says, hey, maybe you have extrema at these x values. The second derivative says, hey, I can tell you what the curvature is around those possible extrema, so you can verify whether or not they're extrema. Then we now know via the original function and the first and second derivative what our local maxes and mins are. So now let's talk about inflection points and finding them. So if we want to find possible inflection points of a function, what we first need to do is set the second derivative equal to 0, and then we're going to solve for x. Then we need to check what does f double prime of a do around x equal to a. So if we want to find possible inflection points, first thing is we need to find the second derivative and set it equal to 0. And then we're going to find the zeros of the second derivative, and then we're going to take a look at those values and things around them. So let's do that. So step 1, find the first derivative. So f prime of x, that's going to be 5 over 20 times x to the fourth. I'm just reducing my fraction in a moment. And then 1/4 times 4, that's 4 over 4 times x to the third. There's our first derivative. We do get some reduction here. That's going to be 1/4 x to the fourth minus 1 times x cubed. We'll then define the second derivative. Well, f double prime of x, that's going to give us 4 over 4 times x cubed minus 3x squared. Then, of course, that little bit of reduction, that's going to be 1 times x cubed minus 3x squared. At this point, to find possible inflection points, that is, set the second derivative equal to 0. 0 is equal to x cubed minus 3x squared. I'm going to factor that 0 is equal to x squared times x minus 3. So then I get two possible inflection points after using the zero product property. 0 is equal to x squared, 0 is equal to x minus 3. So square root of 0 is 0, and add 3, x is equal to 3. So once again, make a note. We have possible inflection points. All right, possible inflection points at x is equal to 0 and x is equal to 3. Now that we have the list of possible inflection points, realize that this derivative, the second derivative, is still a function, and so there's some properties that hold. That is, this function, being a function, is continuous. And so if you want, what you can do is you can then cut up a number line at 0 and 3. And what we're going to do is we're going to plug in values for f prime and figure out, is it negative or positive around these possible inflection points. And so if we get a change in sign around these possible values, then we know that the value is an inflection point and we're done. So let's do this. So specifically, let's pick a value to the left of 0. And so I'm going to pick, how about -1? So what's f double prime of -1? Well, f double prime of -1, that's going to be -1 cubed minus 3 times -1 squared. Well, then evaluate that. That's going to be -1 minus 3, so it's negative. So specifically, I know that to the left of 0, I do have a concave down function because this is negative. Now let's plug in another value, but this time let's pick something between 0 and 3. So how about we plug in 1? So what's f double prime of 1? Well, f double prime of 1 is 1 quantity cubed minus 3 times 1 squared, but that's just going to be 1 minus 3. 1 minus 3 is -2. And so I now know that to the right of 0, the concavity is also negative. Okay, so what does this tell me? Specifically, this now tells me that 0 is not an inflection point. And the reason that it's not an inflection point is because the concavity does not change on the left of 0 or on the right of 0. Now let's pick a value to the right of 3. How about f double prime of 4? That's going to be 4 cubed minus 3 times 4 squared. Well, that gives me 64 minus 48, but that's positive. And so since that's positive, I actually know that to the right of 3, I have a concave up function. And so notice that the concavity changed from negative to positive at 3. And so specifically, 3, x equal to 3, is my only inflection point. Now that's the location. If I wanted to find the exact location, that is the x and the y, I could of course plug it into the function, f of 3, which is then going to be 1/20th of 3 to the 5th minus 1/4 of 3 to the 4th, which then gives me 243 divided by 20 minus 81 over 4, which I claim is -81/10. And so specifically, if we wanted to have that inflection point as an ordered pair, it is at 3, -81/10. And so the location of the inflection point is at -3, but specifically the inflection point is the ordered pair 3, -81/10.